Welcome to HydroMaster's CDS xDrive Service Training Video Series Part 3. In this part we're going to cover the 48 volt system of the xDrive. That's what makes it unique, a different voltage system. We're going to cover the cables and the wiring that are associated with the 48 volt system. We're going to cover the electrical contactors, which are a very important safety part of the 48 volt system. And then we'll talk about the motor controllers themselves and what their function is. So first, the power cables. These power cables are what they call SRML. It stands for silicone rubber motor lead. What that means is the conductor is covered with a silicone rubber sleeve. And then on the outside of that is a fiberglass sleeve. We made it orange so that it could be easily identified, particularly underneath the vehicle, so it doesn't get confused with some of the other vehicle wiring components. It's easy to tell what is the xDrive wiring and what is the vehicle wiring. SRML wire is rated to 400 degrees Fahrenheit, 600 volts it's good for, and a continuous or an operating amperage limit of 392 amps. The conductor itself is copper, but it has a tin coating. Just show you a little bit closer. So each strand of copper wire is covered with tin. The reason for this is that prevents corrosion of the conductor, the copper conductor. If anything were to happen to the protective sleeve, it got a nick or a cut or abrasion so that the conductors were exposed to the air, just regular copper would start to oxidize and you start to lose performance. But in this case, the tin prevents any oxidation. The size of the wire is 1/0. It does have crimped ends, so we crimp the ends on. These ends are crimped on with a hydraulic press at 6,000 psi. Then on the outside of that is adhesive-lined shrink tubing for the entire crimp connection, and so that seals the entire connection from the atmosphere, protects it from the elements. The way the cables are routed on the xDrive is to try and keep them away from anything that would cause degradation of the cables, particularly heat. When the cables come out of the generator, they go underneath the engine to the passenger side, so away from the engine exhaust, travel down the passenger side, and then behind the passenger seat, go up through the floor, and then up into the console. They are routed through and secured with these nylon cable blocks, as you see here. Those cable blocks keep the cables from touching each other, as well as keeping them secure from touching any other metal components, van, and also on the CDS console. So the next cable that we'll talk about is the encoder cable. This is a very important cable because it carries the signal from the motor and the generator back to the controllers so that they can function properly and control the motors. It is a 7-conductor wire, but we do only use 6 of the wires. It is a shielded cable. We'll talk a little bit about what that means later, but it's very important because the signal from the encoder is a very low voltage. It's only 5 volts. So we have to protect that so that no stray interference affects that signal. The colors for this encoder cable are the blue wire is the cosine signal from the encoder, and it goes to pin 35 on both controllers. Each controller has their own encoder cable. The brown wire is the power, or the positive, going to the encoder. It comes from pin 26 on the controller. Black wire is the negative, ground for the encoder goes to pin 15 on the controller. The green and the white wires are actually the 2 wires for the temperature sensor inside the motor. We run them through this cable just because they all come from the same place. The green wire is actually the negative wire for the temperature sensor. It goes to B- bus bar. And then the white wire is the actual signal, the temperature signal, goes to pin 33 on both controllers. The red wire is the sine wave signal from the encoder, it goes to pin 21. The bare wire is actually the shield wire for this cable, and that's what makes it a shielded cable. A shielded cable has a piece of foil, you just barely see the edge of it there. It wraps around all of the conductors, and then over the top of the foil is this bare wire, bare copper wire is wound around that. So the purpose for that is to keep any stray electrical signal from the outside getting into the inside of the conductors on the inside and possibly affecting the signal from the encoder. This bare wire on the controller end of the wire is actually connected to the B- bus bar, so it's grounded basically. A way to think about this shielded wire is to think of it like a lightning rod. Lightning rod on a house is just a metal rod, usually at the top of the highest point in the house, with a wire that just goes down to ground. So if lightning were to strike near the house, the electricity would travel down through the wire and into the ground instead of into the house. So this is kind of the same thing. If some stray electrical signal were to come along, it would reach this conductor and then just go to ground and wouldn't get through the wires on the inside. So those are conductors on the encoder cable. The ends on the encoder cable, each end where it connects to the motor or the generator, the connection is made with a 6-pin Deutz conductor. So this is the shielded wire. It comes out, it goes into the connector, but then we also seal that exit point from the conductor again with an adhesive lined piece of shrink tubing, so it's all sealed again from the environment. So each of those pins is inserted into the back of the conductor, is crimped on individually, and they can be removed, so they can be repaired easily. And each wire is pushed into the back of the Deutz connector through this watertight connection. So the pin just pushes in through the seal and then engages to a lock that's on the inside of the connector. And there's a couple of instances in the system, not in the 48-volt system, but in the regular CDS system, where one of these pins doesn't have a wire coming into it. In that case, we do have to put in a blank plug to make this actually a watertight seal. To make sure those blank plugs are in place. Conductors go into the back of the housing. Housing is actually, each position is numbered, and you can associate the color with the position, and these are all also on the wiring diagram. So position 1 is the black wire, position 2 is the brown wire, position 3 is the white wire, and it goes straight across to 4, which is the blue wire, 5, the red wire, and 6, the green wire. So each of those pin positions is also highlighted on the wiring diagram, so you can get those back in the proper locations. And then once all the conductors are pushed in, then there's a locking piece. You can see the little locking piece over here. The locking piece is pushed in, and that keeps the pins locked in position. So the pin positions again, black wire is pin 1, brown wire is pin 2, white wire is pin 3, blue wire is pin 4, red wire is pin 5, green wire is pin 6. And then it's not shown in this, but that bare shield wire that was in the previous slide is actually comes out and is connected with this green wire because they both go to the same place. So if you see the bare wire coming out and going into the back of this connector, that's okay. That's where it's supposed to. It's just connecting that shield wire to ground. So let's talk about now the line contactors. And the primary function, really not the only function, but the primary function for the line contactors is for safety. So in the case of a three-phase system, only two of the phases need to be interrupted to stop the flow of electricity. So in our case, we interrupt or stop phase 1 and then phase 3. So these line contactors act like just a large remote on-off switch or a relay. They prevent electricity from traveling down the cables. This is important for the xDrive because the generator does not have a clutch. So what that means is the generator is spinning whenever you're driving the vehicle. And even though the generator isn't active, the controllers aren't on, they're not telling the generator to produce any energy. But since there are magnets in the generator, in the armature and the stator, just the fact that they're spinning against each other, it's going to produce a little bit of electricity. So the contactors are in there to stop that from going any farther than right up in the front where the generator is. The contactors, when they are controlled, so during operation, they are controlled by the master controller, which is also referred to as node 1. If you're looking in the front of the machine, it's the controller on the left. And those are pins 3, 4, 11, and 12. So those are the pins that operate the contactors. The contactors themselves are hermetically sealed, so they're completely welded up. Everything on them is stainless steel, so there's no way for them to corrode, or water gets on them. It can't hurt them. They are in fact IP65 rated, and that's for temporary immersion in water for 30 minutes. The contactors are located in a sealed box under the radiator of the van, real close to where the generator is mounted on the engine. This is to keep them cool, but also to keep them protected from the environment. The mechanical life on the contactors is 300,000 cycles. So just put that in perspective. If you were to turn the machine off and on 15 times per day, you'd get about 100 years worth of life out of them. So very good life on these. You can operate to 257 degrees. And they are driven again by the controller. They are 48 volt contactors, but the controller will start them out at 48 volts, so that's what engages them. But once they're engaged, they actually hold with less voltage, so the controller cuts the voltage back to 24 volts just to keep the temperature down. So if you're ever to measure the voltage going to these contactors from those pins coming from the controller, 3 and 4 and 11 and 12, you would read 24 volts and not 48. So there is one failure mode that I can show you with these contactors, and it's not actually a fault of the contactor, but the connection. So if the cable isn't tightly connected to the contactor on those studs on the top, if it's not torqued properly and the cable end is a little loose, it will actually build up some resistance and build up heat. So that's what you see here. This side, the A1, the positive side, was loose, and so it built up heat where the cable end was attached to it, and it eventually caused the contactor to fail. But again, that wasn't a fault of the contactor, but of the connection. So you need to make sure those connections are tight. Now let's talk about motor controllers. Motor controllers that are used on the xDrive are primarily designed to work with batteries and driving small electric motors, golf carts and small utility vehicles. So primarily their use is converting DC, so power from a battery, to AC, three-phase AC, to drive a motor. And that's what we use them for, to drive our motor. But we don't use a battery pack. We actually use the generator to create the power and feed the DC power to the motor controller to drive the motor. So this is kind of what the system looks like. We've got two controllers. They're identical controllers, but they're programmed differently. So the controller on the right is the motor controller. That's the one that's driving the motor, that's spinning the blower and the pump. That is acting as a inverter. So that's a DC to AC inverter. So it's taking the DC power from the DC bus and converting it to AC and driving the motor. So it's controlling that motor, controlling the speed and the torque output of that motor. But to get that power, we're using another AC motor, but we're using the same controller. But in this instance, it's actually converting the AC to DC. And the way the controller can do this is it has a feature, allows it to regenerate, is the term that they use. So it's like in a electric vehicle or a hybrid vehicle, when you step on the brakes in a hybrid vehicle, you're actually turning the motor into a generator. And it's producing power to recharge the batteries. So we're using that same feature in the generator controller to create DC power. So there is no battery pack. We do have a small capacitor pack in line with the DC bus in order to create some filtering and also to supply the initial power to start up the controllers. So as you can see here, the right-hand controller is the motor controller. It produces AC, three-phase AC power to drive the motor. And the controller on the left is the generator controller, which is taking the AC power that's being created by the generator and turning it into DC to supply the other controller. That's kind of the basics of how the system works together. But a little bit more about the three main mechanisms that the controllers use to control the power being consumed and the power being produced. So the first one is voltage. These controllers are 48 volt controllers. That's the nominal voltage that they're designed for. They can operate up to 52 volts, but their maximum voltage where they will completely shut down is 79. So we run about right around the 52 volt mark. So we're running at peak voltage for these motor controllers. So the motor controllers can control the voltage, and this is important, and we'll talk about this later, but they can control the voltage by applying current to the motor. So that's how the motor controllers, that's the only way the motor controllers have of controlling the voltage, is by doing something with that power. And in the case of the xDrive, it's spinning the blower or spinning the motor that's driving the blower. So that's how it controls the voltage. The motor controllers can also control the current. Now they're capable of sustaining 280 amps continuously. They can, for very brief periods of time, produce up to 650 amps. But the current is controlled in order to maintain the speed of the motor. So the motor controller adjusts the current in order to keep the motor spinning at the same speed. And they also control the torque. The controllers are set at 40 newton meters or 30 foot-pounds of torque, which is enough to spin the blower up to full speed and under full load. So the generator controller is controlling the torque of the generator. So that's how it's telling the generator to apply torque in order to create the power. So the controllers have a number of different inputs. The main inputs are the 3 phase cables that are connected to the generators. Those are the big yellow cables. And they are attached to the controllers on the 3 different phase lugs. They're designated on the controllers as M1, M2, and M3. We've color-coded them. So M1 is blue, and if you look at the cables, one of the cables will have a piece of blue heat shrink around the end of it, so you can tell which one is the blue one. The yellow one's the same. The black one is just left without anything, so that you know that that's M3. And the order of these is very important. You can't swap the order of them. You can't put the yellow cable on M1 or the blue cable on M2. If you do, the motor won't run. So on the DC side, so that was the AC side. So the 3 phase cables coming in, those are AC. The DC side has 2 components, 2 parts to it. There's a B plus bus bar, so that's the big copper bar that goes between the 2 controllers, and a B minus bus bar. So this is where, in the case of a battery system, this is where the battery cables would be connected. So this is the DC bus. So on the B plus, or the positive DC bus, there's actually 2 wires connected to the bus bar. There's a red wire, which is the power for the voltage gauge that's on the dash, and then there's a blue and a black wire, which is used to power the on-off circuit that turns the xDrive off and on. And then there's also the red, it's like a battery cable that's coming from the capacitor pack. So that's the positive DC bus bar, B plus. B minus, so this is the negative side of the DC bus. There's 6 wires connected to that bus bar. There's 2 black ones. One is the digital switch for the controllers. The second one is the ground for the voltage gauge, so those are the 2 black ones. The blue one is the ground for the CAN communication plug. The white and green is the ground for the speed switch. Solid green is the ground for the temperature sensors in both the motor and generator. And the white is the ground for the tachometer. Then there's also the black, it's like a battery cable, which is connected to the negative side of the capacitor pack. So those are the connections to both the AC side and the DC side of the controller. It also has a large 35-pin plug at the top, which is where all the control connections are made. That's a 35-pin Amphenol amp seal connector. And there's several different sets, I guess you might say, of connections. One is the encoder cables come to this 35-pin. That's what provides feedback to the controller, tells the controller what the speed of the motor is, what the angle or exact rotation of the motor is. And those are connected to the controller on pins 15, 26, 21, and 35. There's also the connection on that 35 pin for the temperature sensor. That's pin 33. Remember, the other side of the temperature sensor goes straight to the B minus bus bar. The next one is the speed switch. So every time you turn the switch on the front to change the speed of the blower, it's actually changing which pin on the controller is being activated. And those are pins 18, 19, 30, and 31. It's important, if you're doing any work on those particular wires, that you don't apply any voltage to those wires, because they are negative wires. They're connected to the negative side, internal connections in the controller. If you put power to them, you could damage the controller. Then there's the input for the when you turn the switch on, that turns the controllers on. That's the pink wire. That's goes to pin number 1, and it's controlled by the 12-volt relay, which is CR3. The CAN, so the communication wires. So there's the controllers talk to each other. Also, it's the communication for connecting the the laptop or the computer, and also for driving the tachometer. Those CAN communication wires are purple and green, and we usually twist them together. You can identify them that way. But they attach to at least the generator controller in pin 13 and 24 and 16 and 27. And then on the motor controller, it's just pins 16 and 27. So a little bit more about the CAN, or the communication network. This is a standardized electronic communication language. In cars, the CAN communication language is OBD. That's the one that you usually hear about. But cars can have up to 20 different CAN processors. So there's a lot of interaction going on the CAN. And they all need to communicate together, and they do that over the CAN networks. Our controllers communicate with each other over a CAN network, and the protocol CAN language that is used in the case of these controllers is called CAN Open. In our CAN network, we have two what they call nodes. Node 1 is the generator controller, so that's the controller on the left. And node 2 is the motor controller, which is the controller on the right. Node 1, or the generator controller, actually controls node 2. So that's how they're set up. They communicate with each other, and most of the settings are put into node 1, or the generator controller, since it is what they call the master. The CAN communication speed is 250,000 hertz, so very fast. The tachometer is also driven off CAN. The computer interface, so the little computer port on the side, is also driven off the CAN. There are two different ways that we have wired that CAN communication. On the older units, there was actually a plug in between the two controllers. You had to unplug them, and there was an adapter went in to hook up the computer. But on the newer versions, that communication port is actually on the outside, right above the fuse box. So we don't need that adapter anymore. We don't have to take the cover off. You can get to it right from the outside of the thing. So the motor controllers are air-cooled because they're not 100% efficient. Close, but not 100%. They do produce a little extra heat. So because of that, the controllers need to be cooled. The controller itself has a large aluminum plate on the base of it. That's a heat sink that's used to draw the heat away from the electronics on the inside. So we actively cool the motor controllers by means of the air that is coming out of the recovery tank and going through the blower. In this image you can see the inlet for the recovery tank is here, goes into the recovery tank, goes across the recovery tank, comes back through this channel on top, goes down into this box in the front, and then through this box down into the blower. And so inside this box, which the controllers are mounted to, is a large heat sink, a finned heat sink. So as the air is passing through, it's cooling that heat sink, which is in turn cooling the bottom of the motor controllers, and that's how we heat away from controllers. The controllers are mounted to that box to increase the thermal capacity, or the transmission of heat from the bottom of the controller into our heat sink. There's actually a thin film of what they call thermal paste on the bottom of the controller. That's to fill up any gaps that might be in, so there's no air. Air is an insulator. We don't want it to insulate. We want it to conduct heat. So there's this thermal paste that is used when attaching the controller to the heat sink. That thermal paste, the thermal paste that we use is a Dow Corning 340. You can use any number of thermal paste. They are rather expensive though, so we've chosen one that isn't the most expensive, but it works very well. The manual that comes with the controllers use these two images on the right here as an example of what the back of the controller should look like after you've applied the thermal paste. So what they're trying to show here is that it's completely covered. The entire back side of the controllers is covered with this heat sink or this thermal paste, and then just showing that it's again completely covered. Just a note, these thermal pastes are very messy, and if you get them on in your clothing, you probably will not get that out. It's a very aggressive type of material. So that helps to cool the motor controllers as well. So that's the motor controllers and some of the 48 volt system components. And next time when next video, we'll talk a little bit about how to program, or the program that is actually running on these motor controllers.